yeah.
Oh, and I'll hide this little thing there so it'll keep going.
Okay, yeah, so it doesn't freak me out.
Okay, and we'll have
all the way up, and then just hit
keynote
play.
live or play. Okay.
Yeah, it should be, I think.
Okay. All right. Can I have everyone's attention? I want to introduce our speaker for today. This is Greg Morrison, coming to us from University of Houston. This is his first time giving a talk here for our seminar series, so hopefully this is going to be a very good experience for him, and he'll be happy to come back in the future. He is an assistant professor in physics at the University of Houston, and he has a PhD from University of Maryland, where he studied biophysics and statistical mechanics. He did postdoctoral work at Harvard University, where he focused on information theory and biological networks. He also spent some time in Italy. And so he's had a lot of different research, mostly spanning the work of single molecule biophysics. As you saw last week, there was a talk about how the brain works and how the individual neurons work within the brain. So I think this is going to be very complementary to that. Also, I do want to let you guys know I am going to pass around the sign-in sheet, so expect that. And also, I do need to hand back papers. So that I'll turn it over to Dr. Morrison.
Well, thank you very much. Thank you for having me. For those who are watching at home, I'm impressed that at 7 p.m. you're watching someone give a talk on neuroscience. So thank you for tuning in and turning off Netflix. So I do have a background in single molecule biophysics. I'm not going to be talking about single molecule biophysics, though. I'm interested in biophysics in a lot of different contexts, and this talk is mostly going to cover network science and how one can understand the global properties of a highly densely connected network like the brain, given some very simple rules. Okay. The organization of the talk, just to give you a sense of where we're going. So the first thing I'm going to talk about is describe a bit about how neurons work, how the brain works, and some important features in neural dynamics. I'm not going to assume that you know very much about how neurons work, and it is the case, though, that a lot of this is complementary to what Dr. Chung, I believe, talked about last week. She talked about calmodulin, is that right? And so she's working at a very high resolution. I'm going to be working at a very low resolution. Okay. I'll also talk about how we model these neurons mathematically, and how essentially heterogeneity in the context between these things can lead to physically relevant correlations in the firing patterns of these neurons. Okay. Those communities, though, I'm going to show can, if you choose them poorly, can lead to what's called a breakdown of the balance condition and lead to completely unrealistic and unphysical firing. And then I'll talk about how we can actually recover that balance. And so I'm going to show that we're able to recover that balance, and also that recovering that balance is actually not what we want to do. The brain can't be balanced in order to have the kind of behavior that we want. And so I'll talk about how we can break that in a controllable fashion to recover physically meaningful behavior. And then finally, I'll talk about hierarchies in these networks, and talk about how we can send signals from one side of the brain to the other, which is really a fundamentally important feature of neural networks. Okay. Oh, I said the word neural networks. How many people have heard the word neural networks before now? Right. Have you heard it in the context of brains, or have you heard it in the context of machine learning? Both, yes. So I'm going to talk. I'm going to condense the machine learning side of things down to 45 seconds or so, and so hopefully I will mention that somewhere around here. Hopefully it's clear and of interest. Okay, so let's get started on biologically motivated networks, though. So first, I'm going to try to motivate why it is that we might care about these things and what sort of data is available. So this is a picture of a person with an EEG, a micro EEG on their head. Essentially, this device is able to track an electrical signal at all of the different locations along this brain. Each of these lines corresponds to one of these sensors, and this displays the electric signal at any of these points in this person's brain. This person has epilepsy. Epilepsy, as you may know, causes one to have seizures randomly. this is likely, although not certainly, likely not a full seizure that you're seeing, but simply a heightened activity within the brain where you see essentially this relatively quiescent behavior right here that suddenly starts spiking wildly, right? This black line is sort of an overall measure of the electrical activity in the brain and says a lot more activity happening. And each of these lines talks about the behavior very on a millimeter scale within the brain. Okay. There's a couple of features that that I want you to take away from this. First of all, some of these lines are completely flat. Okay, if you're having a seizure, your entire brain doesn't light up, right? Only certain parts of it do. Second of all, you can see that there are differences between these things, right? So here, let's see. This blue one is lit up very brightly, completely missing here. There are some other features that you can see. These guys are much lower here than they are here, and so you could see that the behavior of individual neurons isn't what drives this. This epileptic behavior. Right? There's significant trial-to-trial variation in the behavior of individual neurons or individual regions in this case. But we still see the same qualitative picture, right? We still see that the brain is behaving in a similar way. Okay, so it's going to be important from this picture to understand the global properties of this thing, the global properties of the brain, without focusing solely on a single neuron, right? We need to look at the statistics of this thing. Okay, there are other mental health conditions, so schizophrenia, a few others, that have been shown to have this sort of behavior as well, where there is seemingly a structural deficiency that can lead to these mental issues, to these brain-related issues. Okay. Oh, and before I go on, do please interrupt me if you have questions. I'm happy to answer questions at any time. Oh, I cannot, but hopefully someone can.
What are you asking about?
Is this?
Oh, I can do that.
Yeah, I don't want to. I'm worried that I'll lift up the projector screen, so I will. I'll move on. Okay. Okay. So this is EEG is great. It tells us something, but it only tells us sort of about perhaps at the outside of the brain or something along these lines. A much more three-dimensional representation of the dynamics of the brain can be measured using what's called FMRI, which is functional magnetic resonance imaging. And essentially, in this particular set of pictures, which I'm sure all of us have seen something like this on some TV show before, where you're able to see the behavior of a patient's brain or something along those lines. This is real technology that is commonly used to essentially track the blood oxygen level at different regions of the brain in real time, essentially. So this means that if there is a particular region of the brain that is being active at that time, it needs more oxygen to function. It's a cell. It still needs blood to come and go and deliver it the oxygen that it needs. And so these things are correlated with activity. Now, one thing I want to point out is that these aren't telling you anything about individual neurons, right? They're telling you about big regions, millimeter, centimeter regions of the brain, and how they're behaving collectively. Okay. Alternatively, we can look at what's been called the Human Connectome Project. This was begun in 2009, and it's just unbelievable the sorts of things that they're able to do now. But by combining dissection, which is obviously not good for an individual, but is good for science as a whole, we're able to essentially determine the connections between individual regions of the brain to other regions of the brain. And these are much closer to an individual neuron level. Okay, these are micron scale. So these cells, though, aren't necessarily going to be micron scale. So these are still long range, somewhat larger connections, but we can draw these connections between different regions of the brain at incredibly high precision. Okay, and this sort of data is available for humans, mice, and a few other organisms. And so this really opens up an enormous amount of ability to study the global behavior of the brain. And one feature that I want to point out here, so you can sort of see that these bundles of filaments between different regions of the brain, they're sort of clumped together, right? You can see that some of them are bound together and then there are gaps between them, right? This is because regions talk to regions. You don't just have a uniform connection across the entire network. We can do actually a bit better than this, though, and we can do so by essentially designing systems that allow us to measure the activity of individual neurons within an individual's brain. So, unfortunately, you have to cut into the person's head, which is why this is not too often used in humans, but it is for those that have these brain conditions. More often, we use model organisms. This is in this particular case, what is this? This is a salamander. This is the visual cortex of a salamander, essentially, that is put on a petri dish, basically on top of one of these things, and the electrical activity of every single neuron is monitored. That's what all of these dots are, and then this image is the image of another salamander. It's a picture of another salamander that they're showing the visual cortex of this first salamander in the petri on the petri dish. Okay, so that's what this is. What you're seeing in this next figure is essentially where these arrows are point to the particular location that's being monitored. This is as a function of time. Once you turn this image on, what is the response of the neurons along in between these two arrows? Okay, and what you see is after about 50 to 75 milliseconds, nothing's happening. There's a lag time between seeing something and being able to respond to it, which we've all experienced. And then what you're seeing is there's extremely highly correlated firing that indicates that something has been seen. Right? If you look at the lag between the time of first firing for all of these things, this is what the visual cortex reconstructs. Right? The latency of this, that's what this latency is. 0 means that it fired at the average time. Negative, which is dark, means that it fired earlier than expected, earlier than average. And white means that it fired later than average. This latency encodes the information for what it is that this visual cortex is looking at. Okay, and we can monitor this in real-time neuron level. Okay, let's see. A couple of other things to say. Let's see. So one thing to point out. Essentially, you show this visual cortex a picture. That picture is going to be registered essentially simultaneously. So there is this variation that gives you the information, but this is all very synchronized. It's not really random, right? You see this information is built into this. It's possible to have asynchronous information, being asynchronous transfer of information or transfer of stimulation, where the firing rate is increased in certain regions of the brain, but it's not synchronous, essentially. So there is a relationship between firing. There's a lot of firing going on, even if it's not timed perfectly. Okay, so we're going to actually in this talk mostly be interested in asynchronous correlation, which means that we stimulate something and downstream something else gets really excited. Okay, but it doesn't have to occur at the same time. Okay, so those are some motivations. What is it? So I said the word neuron a couple of times, and I'm not sure how deeply Dr. Chung got into this picture, but it's definitely worth talking about. So this is a picture of a neuron. This is what's called a presynaptic neuron because it has a large axon that is connected here to what's called a postsynaptic neuron. Essentially, this neuron is going to send a signal along the axon to the neuron at the other side, and that's the difference between pre and post. The neuron that sends a signal is presynaptic. Okay. So the way that a signal is sent is that there is the cell is composed of a membrane. This membrane has ion channels. These are either potassium or sodium. And essentially, if the cell reaches a certain potential difference across this, which is greater than its resting potential. So at rest, there's going to be some equilibrium potential difference across the membrane. As positive charge flows from the outside to the inside, it's going to take on an additional positive charge in here, and that if the potential difference is, if the change of the potential difference is large enough, it causes a cascade, where suddenly the sodium, let's see, so the sodium channel opens up, and sodium from outside rushes in, driving the potential difference to become more and more positive. Okay. That signal is once that becomes high enough, then the potassium channels open up, and all the potassium is released. and that is it. So the entry, rapid entry of sodium is called a depolarization, and then polarization is when the potassium is pumped out to recover the resting potential difference. Okay. Once that happens, that process will propagate along this axon. So each of these along this axon, there are all these different channels, and if we have a depolarization event here, I need to switch my pointer, I think. Well, we'll see. Whenever we have a depolarization event here, essentially it'll repolarize. But because this was depolarized, there's going to be a positive potential difference across the next segment of the membrane, which means it is going to depolarize. And then it's going to try to repolarize, but it's going to pass that signal of depolarization along. And so there's this cascade, there's this sort of avalanche of depolarization and repolarization that sends a signal from the presynaptic neuron to the postsynaptic neuron through this axon. Okay. This is an all or nothing event. Either this, let's see, so either this depolarization wave propagates or it doesn't, right? So you can have little fluctuations in the potential here, but if there's not this depolarization wave, there's not a signal sent to the other neuron. Okay. How does this work? So this is a schematic of the depolarization wave. Essentially, this is sort of, you can imagine these are the depolarization events where calcium is flowing, and this is whenever the the wave hits the end of the axon, essentially, neurotransmitters are released, and they can be detected by other neurons. And so this is a chemical signal that's driven by this potential difference in the axon. Okay. Those neurotransmitters are things sort of like, so glutamate is one of the more common ones glutamate is commonly used to send an excitatory signal from one neuron to another, and GABA is another neurotransmitter that sends an inhibitory signal. Okay, but there are lots of these neurotransmitters, dopamine, adrenaline, a lot of things that you've heard of before as well. Okay. Essentially, the process of receiving this signal is a complicated chemical process as well. There's diffusion of these neurotransmitters to reach the receptors at the postsynaptic neuron, and that process is strongly related to what Dr. Chung was talking about before. Right. So this is the scale that y'all heard about last week, and I'm going to be interested at the much more global scale of the kind of data that we can get from the human connectome. Okay. All right. So how do we model this? So in order to mathematically model these things, there are many steps that go into this process, right? There's from the calcium and sodium, from the calcium and sodium pumps all the way down to potassium and sodium pumps, all the way to the propagation of this wave, and then the chemical process that underlies it. All of that is very complicated and difficult to model simultaneously. And so what we're going to do is use a much simpler model, which is called a leaky, integrate, and fire model. Okay, leaky, integrate, and fire model means that we're going to pretend like the neuron is just a ball in space, and it's got a connection to other balls in space. Okay, we're even going to ignore that right now. Right, we've got just some sphere, and it has a potential associated with it. That potential has some rest value that it likes to sit at, and it reaches that rest value exponentially. Right, so it exponentially decays either up or down. If its potential is too high, it decreases the potential. If it's too low, it increases the potential. And we're going to model. So that is the dynamics of the potential of the leaky, integrate, and fire. With one exception. If the potential is high enough, it fires. And what it's going to do whenever it fires is drop. So this is what the dynamics is going to look like. The potential drops to 0 and stays at 0 for some amount of time, which is called the refractory period. And then once it's after that refractory period, it's going to return to its usual dynamics of exponentially, in this case, growing from 0 to whatever its rest potential is going to be. Okay. So this means that if we just have a neuron sitting around, and as long as it's the rest threshold is great, rest potential, the potential it likes that, is greater than the threshold potential, the threshold at which it fires, we're going to have regular, like clockwork, firing of this neuron. Right? It's going to continually increase up to the threshold, then drop. wait for a little while, increase, then drop, and so on and so on. Okay? So this is the sort of dynamics that we expect. But that's for a neuron that's just floating in space, living by itself. Right? In order to account for any external signal or any interactions with other neurons, we're going to add a synaptic current, right? Which is just going to be, this is this DVDN is the normal dynamics, and then there's going to be something that comes from outside. What's going to be coming from outside is we're going to focus primarily on the synaptic current being driven by other neurons in the network. So we imagine that we've got a whole bunch of these neurons, these idealized spherical neurons, and that's what's represented here. Each of these dots represents a neuron, and each of the lines represents a connection between them. Okay. In this particular diagram, they're completely randomly connected. There are, in this picture, 4,000 neurons, or supposed to be. This may be scaled down to make it visible. But there are 4,000 of these exciter neurons and 800 connections between every neuron, right? So every neuron is connected to 800 others in the network, but it's completely random. And this is the sort of behavior, or the sort of picture that you should see from this for this network is essentially this ball of hair where you have lots of connections and there's no real structure. Okay. So how do these things talk to each other is one of the last things that we need to talk about, right? So this is the synaptic current at neuron N. It's going to be composed of two pieces. One is an exciter piece, which is going to be multiplied by JE, that says anytime some other neuron that I'm connected to fires, I get a signal, right? And so I'm going to add to my potential, the time derivative of my potential, I'm going to get a jump, essentially. And the size of that jump is going to be JE, this exciter signal. Okay, but there's also inhibitors in the network. They're connected, and anytime one of them fires, I reduce my potential. Okay, so there's going to be a drop in my potential. Okay, so like I said, there are these things. So these are the number of neurons, the number of exciter neurons, the number of inhibitor neurons, and then this is the probability. Okay, and this is the sort of dynamics that you see. So this is a plot of the potential of a particular neuron. So we're going to imagine just one neuron tracking it. And what we see are these depolarization, these firing events, essentially, where the potential suddenly drops, right? And then it builds back up and it floats around for a little while and then it drops again. Okay. We can visualize these individual drops, right? There's a lot of noise here. We can visualize this more efficiently by drawing what's called a raster diagram. This is the time of this is the time running from 0 to 2 seconds, and this is the neuron index, right? So neuron 1 is down here, neuron 4,000 is up here, and every one of these dots corresponds to one of these firing events, right? So every time it fires, we draw a dot. Okay. So if one was firing, if they were all firing synchronously, what you would see would be straight lines, right? Everyone fires at whatever time this is, and then everyone fires at this time, and so on and so on. Okay, so a couple of features to see here. Looks random, right? A fun thing actually is there are a few pictures that we're going to show you that I'll show you where you might be able to convince yourself that it's not random, but it is. So you might actually convince yourself. Does anyone see that it looks a little bit lighter here? Yeah, random. It's just dumb luck. So all of these are going to have weird features, and your brain is really clever. It tries to tell you that there's something there, and it just isn't. So it's always fun to look at these things, just because they can be random, and you will see something in them. Okay, but this picture says that the brain is essentially this model brain is firing randomly, and there's no structure whatsoever to it. Okay, before I go on, I just really briefly want to talk about neural networks in machine learning sense and tell you why they're different than what we're talking about. Okay, so a neural network in a machine learning sense it's a machine that tells you whether or not a picture is of a cat or a dog, basically. There are hundreds of applications of these things, but at its most basic, it takes in data at what's called the input layer. It does something to that data. Right? Whatever it does to that data, it sends it downstream to what's called a hidden layer, and that hidden layer processes it somehow. Essentially, it takes the pixels here, and it averages them or swaps them around or does whatever it's going to do. But essentially, it sends a signal from the input layer down to one of these hidden layers, and that can pass to another hidden layer, and that can pass to another hidden layer. And then at the end, it has an output layer that says this is a cat or a dog or an airplane or a bus or whatever you like. And it's unbelievable the stuff that they can do. It's incredibly accurate in some cases. It's a really remarkable system. What we're going to so the important thing about this is that you take data, you take 100,000 pictures of cats, 100,000 pictures of dogs. You say one's a cat and one's a dog, and then the computer teaches itself what is the correct way to connect each of these layers to recover cat or dog. That's essentially what's going on. We're doing things that are different with this. One is that we're going to be interested. Let's see. One is that we're going to have positive and negative connections, and that's true here. We're going to have a positive connection here, negative connection there. There's no problem with that. We're though going to be for real neurons. They either spit out exciter neurotransmitters or they spit out inhibitor neurotransmitters. They don't do both. Right? So neurons have to be one kind or the other. We care a lot about dynamics. Whenever I have one of these neural networks in the machine learning sense, essentially I send pixels from here to here, and then from here to here, and then from here to here. For neurons, all the signal can pass in different times, right? And it makes it a big mess. It makes it very hard to extract information. And then finally, whenever you built this thing, you handed it cat pictures and dog pictures, right? So if I show you an elephant, it's going to say 50% cat, 50% dog, because it doesn't know what to do. Right? Our brains aren't like that. We're not optimized on a single training set. And honestly, we're probably not all that optimal, as anyone who's gone into a room and said, I have no idea why I went into this room knows. Right? Our brain doesn't do everything perfectly. Right? And these things are designed to be as perfect as possible. Okay, so neural networks are amazing. It's not quite what we're talking about here. Okay, how are we? Okay, one other mathematical thing. So I mentioned that these things were random. What do I mean by random? Right? So a Poisson process is one where you have essentially an exponential distribution of the time between events. Right? So sometimes things happen close together, like these two lines right here, and sometimes they happen really far apart, and that's just random chance. Okay? So a Poisson process is what we're thinking of whenever we think of random. And if we just had one of these idealized things sitting out without any connections, it would be a Poisson process. Essentially, the firing would be exponential, would be random when distributed. If the network matters, though, we kind of expect that it's not going to be a Poisson process. Right? We expect that it's going to behave a little differently than just perfectly exponential. And so we're going to monitor the behavior of this network using two things often. One is the firing rate. Right? The activity of the neuron is going to matter. But also we're going to be interested in what's called the Fano factor, which is the variance divided by the mean. Okay. And it's a nice feature of the exponential or a Poisson process is that it has a Fano factor of 1, which means that if we ever see something, if we see a Fano factor less than 1, our signal is more organized than exponential. Right? And if it's greater than 1, then our signal is more noisy, has more diversity in activity than you would expect by random chance. Okay, so f is less than 1 means that our system is more predictable than you would expect by chance. Okay. Okay. How are we doing on time? So. Okay, so in this picture, we had the worst model for a brain possibly imaginable. Right? We have a whole bunch of neurons that are these idealized things, and then we connect them randomly, which is probably not how the brain is organized. And in fact, it's not. The brain is, neurons are organized are connected to each other spatially, right? Where they are in the brain matters. They're connected between regions, and so the function of the region of your brain has an influence on who you're connected to. If you draw essentially the connections between the long-range connections between neurons, what you see is that you see the binodal structure of the brain. Essentially, this is left side and right side, or vice versa, whichever side 1 and 2, I suppose, where each of these, once again, each of these edges corresponds to a connection between these things. And what this says is that it really depends. There's a much denser connections, denser set of connections here than here, right? You don't have all that many connections that are really long range. Another, let's see, so this is, I want to say this is macaque visual cortex, but I'm not 100% sure about that. Maybe I have it. Well, it doesn't. This is a visual cortex of some creature who's that I can look up. What you see is that there's a much denser set of connections here than there are here, and some of these neurons are highly connected and some of them are not, right? So there's a whole lot of diversity in the structure of the connections between neurons in the brain. So we can take a stepward and say, okay, why don't we include some of that diversity? Where essentially we're going to go from this really, really basic idea to a slightly more complex idea where now we have multiple regions of the brain that are more dense within themselves than between each other, right? So you can clearly see that there's a denser set of connections here, here, and here, right? These are called communities in network science literature. They're called clusters in the neural network literature. And so I'm going to use both of those words interchangeably. And, oh, this is not very clear. So there's lots of firing events that are occurring here, but they're not pictured well. It looks basically like this, right? The firing is still going on, but on top of that, there is these brighter bands, okay? And what's happening here is that so each of these corresponds to a single community of neurons that are clustered like this, okay? And here what we've done in order to make these clusters, we've increased the probability of connecting to one of your friends or one of your same type of neurons. We've increased the probability of those connections by a factor of 2.5. You can increase it by less or more. You'll get roughly the same behavior. It'll be slightly different, but 2.5 makes for a nice picture, so this is what we choose. We also increase the strength, so you remember those J factors. So neurons of the same type are more exciting to neurons of the same type than in comparison to neurons of other type. Okay. And what we see is that sometimes, so this is in this region, which is difficult to see because of this projector, there is very firing or normal firing sometimes, but other times there are these really bright spots, right? And that means that those communities are really lit up. There's a massive increase in the activity. And so this is essentially spontaneous excitement of the activity within these communities. Okay. We can also stimulate these. This is a little bit clearer. You can kind of see that there is actually activity outside of the bright spots, right? So over this band, essentially you see the gray area. These are communities that we've grouped together and decided to stimulate from 1 second to 1.5 or to 1.5, I guess, seconds. And by stimulate, all I mean is that we add a constant value to that, a synaptic current that I talked about before. Right? While it's being stimulated, the phantom factors drop, which means that it becomes more predictable. We're seeing that this thing is behaving more predictably, right? On is more predictable than random, right? And so that's the dynamics that we're seeing here. Okay. An interesting feature of this is that this is the phantom factor for neurons that are directly stimulated. If they're not directly stimulated, so all of the neurons up there, we also see that the phantom factor drops. Right? And what's happening there is that for a somewhat unexpected reason, these neurons are being suppressed. Right? The neurons that aren't being directly stimulated are being suppressed. And the reason why is because the signal, essentially these guys are more excited. So they send a signal to the inhibitor saying, hey, I'm really excited, and those inhibitors inhibit everyone else in the network. And that is, so there's some evidence that perhaps that plays a role in actual brains, but there's also evidence that it doesn't. And it would seem very strange to light up a community and then that turns off everything else in your brain, right? If you see something, you don't want to be incapable of moving your hand or something like that. So it's interesting to see whether or not this is something that we can suppress. Okay, so this is the behavior if we have homogeneous communities. The picture that I showed previously, every community is exactly the same size. So the question that I got interested in, we're finally to the point where this is my work, the question that I got interested in was the heterogeneity of these things. So this is the picture I showed before. There's a very different, these communities are clearly very different. This is another visual cortex of another creature whose name I don't recall. And what you can see is that there's a community here. Every dot here is a connection between these things, like an anatomical connection. So these things are connected in a physical sense. And what you can see is that there's big communities and also small communities. And this is true for most of these brains, most of the brains that have been studied at this level looking for communities of connections between neurons shows that there's a lot of heterogeneity in this. Okay, so I was curious, what does the heterogeneity do? So what we wanted to do, let's have some big communities and some small communities and see what happens. This is the model that we chose. We chose essentially the size distribution to be exponential. So we have some, with some probability, we have a big community. With other probability, we have a small community, and we just randomly generate network, right? And what we see is something bad. So a couple of features to point out. Oh, this is visible. There's blue, then red, then blue, then red, then blue, then red. The blue corresponds to the first largest community. The next red corresponds to the second community. The next blue corresponds to the third, and so on. So it's alternating in color so that you can visualize which one's what. Okay. We also see that everybody is sort of happy and doing their own thing up until about 500 milliseconds, at which point the largest community freaks out, becomes completely hyperactive, and because its activity affects the inhibitors, it completely turns off everything else in the network. Right? This is not good news. If the brain were wired like this would be very bad. Right? Because this happened spontaneously. This is a topology that causes extreme hyperactivity that leads to behavior that would be medically very bad, right? So this was a big surprise. The project that we were starting to work on had already sort of gone off the rails because this was not the expected behavior. Okay. So why does this happen? Well, what's happening is that we're breaking a principle that is called balance. Okay, and it has a particular definition, which means that on average, the amount of excitement that a single neuron receives should be about the same as the amount of inhibition that it receives. If it gets too much excitement, it's just going to keep firing. And if it receives too much inhibition, it's going to turn itself off. Okay. Let's see. Yeah, this I've already said. So for a balanced network, if we were actually this idea of balance, each neuron was going to experience roughly equal of these things, roughly equal excitation and inhibition. And it's been shown, this is something that's well studied, that for a balanced random network, these two conditions should be satisfied. Okay. And some of y'all might be thinking, what's wrong with this guy? Why didn't he balance the networks to begin with? If this is so well understood. We actually did impose both of these conditions, right? We didn't screw up that badly. So these conditions are insufficient to balance a clustered network. Okay. The reason that they're insufficient is because not only do we want the balance condition to exist, we want it to be stable. Okay. So if we imagine that we've got some set of exciters and inhibitors that are evolving under a mean field potential. So here R is the firing rate. Tau is some time scale that we don't know. It's whatever. This is a mean field approximation, so some number. Imagine that the firing rate forgets about what its current state after some amount of time, this time tau, but interact with other neurons in the network with some interaction matrix W, with some function that we don't know. Okay. So this is all that this equation is saying, is that it's some relationship some relationship with the current firing rate and its dynamics. Now, if we assume that we can linearize this function about about the mean field solution for this, which is just going to be these FEs, essentially we see that this differential equation vanishes whenever RE is equal to FE, and as long as these two things vanish. That's only going to happen, though. That's only going to be stable if these things are negative, right? So the solution exists, and it's going to be stable, which means that small perturbations are going to let us stick to that solution if this has negative eigenvalues. If this thing has positive eigenvalues, a small kick away from this solution is going to lead us somewhere else. Who knows where it's going to lead us, but it's going to go somewhere else. Okay? So this is the basic idea with balance, is not only that we impose balance, we need to make sure that the balanced state will be the state that we end up with. Okay? For a clustered network, this argument still works. This is just RE and RI. If we have a bunch of different communities, we got to break them in. Essentially, we have, instead of having two equations, we have C+1 equations. But all we need to do is make sure that we have all negative eigenvalues. Okay? So, sorry for the matrix math. I'm just going to wave my hands a little bit. Don't get too stressed about the number of parameters here. Basically, if we have homogeneous community sizes, then we have a very regular matrix, right? The matrix is going to be some stuff on the diagonal, which is the self-interaction, some stuff off diagonal, which is going to be the interaction between exciters, and then these bottom and side rows and columns are going to be essentially the interaction with the inhibitor. Okay, and we can actually diagonalize this thing. It's actually not hard to do. This is the condition. This is C-1 conditions to balance a homogeneous network. And if we do the same thing for heterogeneous networks, essentially the only thing that changes is that some are bigger and some are smaller, so we have to include these fractions, right? So this says that I increase the connection strength within A by some fraction that's proportional to the number of neurons within that community. Okay, so that's nice, but a problem is that if we pick bad values of f, everything falls apart. The eigenvalues can be negative, and we end up with really badly behaved systems. Okay, so what we're going to do is we're going to say, okay, well, the only reason why that's happening is because we had to scale everything up. We had to scale up our interactions due to the fact that there are more neurons. Why don't we scale down the interaction strength so that we balance that out? Okay, this is not the only solution to create a balanced network, but it's a solution. Turns out it's very easy to do. And so we decided to work this out. These are the conditions that are required. And so it is absolutely possible to construct a very simple weight matrix that allows us to look at balance dynamics in neural networks. And what we see is global synchronization. So clearly, I mentioned earlier, we have these straight lines going up and down, right? That means that almost everyone fires at a particular time, and then waits for a while, and then fires at a particular time, and so on and so on. We got very excited about this. And it turns out that this is garbage. The reason why this is garbage is, this, by the way, whenever you're doing original research and you get excited about something and nothing is working right, it looks like it's ridiculous, figure out why it's ridiculous, because it might actually lead you to something interesting. The reason why this is happening is I divided by fi right here. Right? Well, if fi is really small, then I just increased the strength of some of these connections by a lot. And so that means that if I have a community of just one, right, just one neuron sitting by himself, one lonely guy, the interaction, so let's make that two actually, two neurons that are within the same community, and that's the only size of the community, well, they're going to have an enormous interaction between each other, and they're going to tell all the inhibitors to fire whenever they're firing, and that's going to suppress everyone else, and we get this synchronization. Everybody's inhibited until these two guys aren't, and that's ridiculous. The problem here is that we've included these tiny, tiny communities in our whenever we rebalance the network. And so what we're going to do is throw them away. And we have some mathematical formulas for how we choose what to throw away. But basically, small communities are out. We keep the big communities. And this is finally the firing pattern we see for this balanced network. Essentially, this is the largest community, second largest, so on, so on, so on. Okay. And it behaves reasonably, right? Nothing is going crazy, and we're actually able to see reasonable dynamics here. This is the Fano factor. Yeah, this is the Fano factor saying that if we have these balanced communities, all of these communities are balanced, and they have a slightly lower than 1 Fano factor, meaning they are a little bit more regular. That means there are correlations inside of these communities, more than one would expect by random chance. And then we have these other communities. These are small. All of these guys way up here. They're in small communities. Who cares what they do? But we prevented them from destroying the dynamics of the brain. Okay, so that's fantastic. We actually have a project now that makes sense. So why don't we try? So what we're going to try to do now is stimulate one of these and see whether or not, we're going to stimulate a subset of the neurons within that community and see whether or not we can, what happens to the network. And what we see is absolutely nothing. So we light up this section of the community, which is what this set of points here is, and then we look to see what's the behavior in the other half of that community, which is what that line is, and there's absolutely no response whatsoever. Well, that's not great, because being able to send a signal, being able to respond to stimulus is one of the basic functions of a brain, and so it's a very important feature to have. So what have we done wrong? Well, the thing that we did wrong is balance the network. So all the stuff that I said about the brain needing to be balanced is absolutely true if we want perfectly stable dynamics, right? If we were to have because we have a perfectly balanced network, we stimulate this part of the community, that sends a signal to the inhibitors. The inhibitors say, well, I'm going to inhibit this other part of the community, and because we balanced it correctly, it prevents any signal from going to any other neuron. It prevents this coordination. Balanced networks can't respond to stimulus in this fashion. So what do we do? Well, we go back to this, this stability equation and say we still need negative eigenvalues, but why don't we make, in order for balance to be perfect, we need negative eigenvalues. Why don't we perturb that just a little, right? And what we mean by just a little is we're going to imagine that we perturb these rates, and to do so we perturb the strength matrix. And so to first order, we can work out what the perturbation in the firing rate will be in terms of the perturbation of this weight matrix, right? And we can make that small, right? Doesn't have to be zero. It's just got to be something that's manageable. It's got to be a reasonable number, whatever it is. Okay. So we do that. This particular set of values, in particular, we choose delta W to just be along the diagonal. So we're increasing the positive feedback within each community whenever we do this. And I think we chose epsilon was 0.1 in this case. Small number. You can do it for other numbers and you'll get roughly similar behavior as long as it's reasonably small. And this is what we get. So we still have reasonable behavior, but what we see is we've increased the Fano factor now. So this is what we saw in the homogeneous cluster communities. There's a bit more higher density firing here. Maybe you can convince yourself. Once again, that might be your brain tricking you, but it might also be real. I'm not sure. But it is the case that this is firing in a less coordinated fashion, which is essentially driven by changes in the firing rates. Right, the mean firing rate here is something that fluctuates. Okay, so such that sometimes it's firing slowly, sometimes it's firing quickly. Okay, so this is reasonable, but do we actually see a stimulation? And the answer finally is yes. We stimulate the bottom half here, and we get a response in the top half. And surprisingly, this is something that we were surprised by. The way that we've chosen to balance this prevents us from turning off other parts of the brain, right? You don't see any dip in the firing rate anywhere else, right? So this means that not only have we moved ourselves towards balance and then a little bit away from balance enough that we see reasonable behavior, but we actually prevent some of this non-physical behavior, potentially non-physical behavior. We're still arguing about this. And you can do this to the first and second community, and so it's going to, you can see these, that it works reasonably well. If you stimulate some part, you get a response in the other half, okay? For this particular case, we don't see a one-to-one correspondence, though, right? So the response is always going to be weaker than the stimulus. We can imagine changing the fraction that we stimulate and changing the strength, right? So if I were to grab one neuron and just drive it crazy, that shouldn't necessarily turn on the other 500 neurons, right? And alternatively, if we were to try to stimulate everyone, but with a really, really weak stimulation, nobody would really feel anything. There wouldn't be a lot of change to the dynamics. That's basically what we see. As long as we're above, say, 25 to 30%, and as long as we're in a pretty, for 25 to 30%, we're able we can look at the response of the unstimulated region whenever the stimulus is applied. I'm sorry, this is the response of the indirectly stimulated region in comparison to its behavior whenever the stimulus is turned off, basically. So it is this value divided by that value. Okay. And what we see is that if you stimulate about 30% or so, it's possible to actually get a very clear response from the other half of the community. And this is true for the largest and the second largest community. This is the relative response of the indirectly versus directly stimulated. And what we see is that as long as we're past about 25 or 30%, we can get something on the order of 50% relative response rate. Right? So this is pretty good. We're actually able to see that if we stimulate a community, we get a response within that community. The last thing that we're working on, and this is still, this piece is unfinished, is to understand how hierarchy can play a role. Okay. So this is a picture of the visual cortex for humans. Is this humans? I don't remember. This is another creature whose name I don't remember. Essentially, though, down here is the eye, and up there is the brain. Okay. All these V's are related to the visual cortex. And this is the wiring diagram of the stuff that receives the image and how it passes it upstream so that the brain can interpret that thing. And the important feature here, there's a lot of important features here, but the most important feature here is that this is hierarchical, right? I send the V3 doesn't send a signal everywhere. It sends a signal downstream, mostly to in this area, right? Not everything is connected uniformly. Okay, so if we were to, so a question is, if we take our network, but we have a hierarchy built in where some communities like each other more than the rest of the network, are we able to propagate a stimulus through that network? And the answer to that is yes. What we've done here is we've connected the first and second largest communities a little bit more than the rest. Essentially, we're breaking balance even worse than we were before. And what we see is that if we stimulate 50% of the biggest, we not only get stimulation for the rest of the biggest, but we also get stimulation for the second largest. And likewise, if we stimulate 50% of the second largest, we not only light up all of the second largest, but we also stimulate the first largest. So it's not a function of size, and we are able to share signals between these things. And we're able to do so in a way that respects balance enough that we have physical behavior. Okay, so I am actually pretty close on time because we started a little bit late. Okay, so just to summarize what we talked about, the surprises today were that balance is an enormously important thing and is not easy to impose correctly for clustered networks, right? But if you do impose balance, if you figure out a way to do it, it can't send signals. A balanced network can't propagate stimulus in a way that is physically reasonable. And so it's absolutely necessary to have a nearly balanced but not quite balanced network in order to actually propagate these things. And we can do so pretty reliably. Once we're past about 25%, it's possible to send signals upstream and downstream, or we can do it by connecting smaller communities to the larger one. Okay. A few things to also mention. Our solution isn't unique, right? Like I said, all we did was divide some stuff by this additional normalizing factors F. There are lots of other ways you could imagine to balance this thing. All of them that we've tried now are hard, except for that first one that I mentioned. But that doesn't mean they're impossible. So we're curious about that. Neuroplasticity is something that's important. We learn things. The way that we learn things is by the brain rewiring itself effectively. So if you have this unbalanced state of hyperactivity, does that drive you to balance? And if so, essentially because the neurons can rewire themselves, will the brain drive itself to try to go back to near balanced behavior? There are lots of models of plasticity, and we're still exploring which ones could do that. And then finally, I'm interested in, if you hand me a network, what parts of the brain are important, right? How can where do you stimulate optimally to actually get a response at a particular spot? Okay. So all of these things are things that we're still working on. Okay, and that's all I have. So thank you.
Questions?
Yep.
So in one of your later slides where you had your partially balanced network, you were stimulating part of one community and getting a response in another.
Yep. This one.
That one.
Yep.
Is it my imagination, or am I seeing a small time delay from stimulation?
We're still trying to figure that out. So that is a feature that we see in the yeah. So sorry, the question was, especially for the people at home, The question was, there seems to be a bit of a lag between, I think that's what you're saying, between the onset of the blue and the onset of the red. And if you look closely enough, you can kind of convince yourself that there's also a longer lifetime, although I haven't drawn clearly enough. Essentially, we turn off here and it lives a little bit longer. We're still exploring that. That is something in the homogeneously clustered networks, and we have not shown that that is something that happens for the in this case in a provable way. Other questions? Yep.
I have a clarification question. Use my clearly whenever you said at the beginning, if the level of the brain is highlighted, you mean that more oxygen is going straight to that area?
Yeah. So essentially what this, I have to hop all the way back. Don't have epilepsy. So what's being highlighted here is the response time of this is on the order of seconds. And so it's looking at the average change in oxygen levels, or the average amount of oxygen that's being pumped into this region at a particular time. And so I think that is close to answering your question, but can you repeat your question?
I just want to make sure. So just when a level is, if the level of the brain is highlighted, so
yeah,
it's been stimulated.
Yes.
Right? And so that means that there's more oxygen.
Yes, there's more.
In that specific area.
Yes, exactly right. Yeah, and yeah. So the baseline, all the gray stuff is sort of baseline where there's not extra flow there, but all the reds, I believe. So I believe, although, yeah. So yeah, the reds correspond to a large amount of activity. The blues correspond to a small amount. And so this means essentially that some blood is moving from the blue regions to the red regions. Yeah. Other questions? Yeah.
So, is there anything to do with the right side or left side?
Yeah, so there absolutely is. So certainly we see that this is the case, right? So it is the case. So just a little bit of detail about this. If I take the data that exists in these pictures, right, and I draw lines between these things, and then I just try to lay this out in a reasonable way. So this doesn't have any information about the actual structure of the brain. The only information it has is connections that are known to be between these neurons. And then I try to draw it in a way that makes the lines as short as possible. This is the feature that I see. Now, so this means that the bilobal structure of the brain is encoded into the brain. What it doesn't tell us is what any of these features do, right? So all of the discussion of this is right-brained activity versus left-brained activity, about language versus math, that can be built into this, but we don't have any idea. At this level, we don't have any idea how. Or, yep.
You have the groupings, you have large groupings and small groupings.
Yep.
Before. Is there like limits on how have you noticed any kind of like limits on how big these groupings get, or?
So it depends. So some of the so it's an interesting. There is of course the theoretical upper bound of the number of neurons in the brain, but that's pretty big, right? Largely, the problem that we have is data like this at this resolution is hard to come by. It's hard to actually track the individual connections between neurons. All of the like this picture. Let's see. Like this picture. So these are individual neurons. These are subregions of the brain. So the connections on this scale are hard to come by on the single neuron level. And so there is no known upper bound, I would argue. And I would argue that it's because we have no idea what the upper bound could possibly be. Because we simply don't have the ability to look at that many neurons simultaneously. Yep.
Whether the body's in like a sympathetic or parasympathetic state have anything to do with which neurons are
I don't know parasympathetic what.
Or, like flight or fight.
Oh, so yeah, so essentially your emotional and mental state has a huge impact. That is something that that's something that people can see in EEGs, I'm sorry, and FMRI. It's also there are lots of studies looking at the difference between resting sleep and active sleep, and you see radically different patterns. I I didn't include the slide, but I was thinking about doing so. Essentially, during REM sleep, you see some regions of the brain are completely silent, and other regions are just happily doing whatever it is they want. And then during active sleep, the other regions have no reason to calm down. And so, yeah, you see very different behavior depending on your mental state. Yeah.
Trauma, physical or mental, can rewire the brain. Does that affect how we connect to each other?
Yeah. So the way that they connect to each other, it is not clear. So basically, the way that the brain rewires itself, the current thinking, as far as I understand, although I read something 2 weeks ago that suggests that maybe this isn't true, but it was only 2 weeks ago, so I can't say if it's right or wrong. The current thinking is that generally the wiring here happens whenever you're a child. And you develop the wiring that you develop, and then the strength of the interaction here, essentially the ability of the neurotransmitters to either send or receive, is the thing that strengthens or weakens, building up memories. Right?
Kind of like adjusting your weights in a computer.
Yeah, exactly right. Yeah, which is how learning stuff works too. That's, I believe, the current understanding of how the strengthening and weakening happens. And so if you have a traumatic situation, particularly an injurious situation where you can break some contacts, that can completely interrupt not only this individual neuron's behavior, but every neuron that's a few steps away from it. And so you can have radically different behavior due to an injury or due to trauma. Yeah. So. Yeah.
Going back to towards the end, I don't remember what it was, but whenever you said the largest cluster affects, whenever you highlighted the second largest right above it?
Yeah.
And you said the second largest also affects the first largest. Does it affect the third largest?
So we designed it so that it wouldn't. What we designed is that, let's see. Yeah. What we did was, if you imagine this picture, we have all of this stuff, and then we cut all of the lines up here. So we still have these guys, we're looking at these guys and they're talking to each other, but they don't talk upstream, right? Any more than they would by random chance. Right? So the only reason that it speaks to the first and second largest are affecting each other is because we built it that way. So what we're working on though, I mean, it's a really good question. What we're working on is building up a hierarchy where essentially we have, so for example, these guys talk to each other and these guys talk to each other. Yep.
I kind of have a follow-up question on that. In a true hierarchy like this, would you end up with a situation where stimulating region 1 causes region 2 to stimulate, but stimulating region 2 does not propagate back down the hierarchy to region 1?
Yes, that is definitely possible. It breaks the symmetry. So basically, you would need to have arrows on this, and that's certainly possible. I'm interested in also, if you imagine, so I've got this stuff. If you imagine that I also have, say, a different eyeball over here, this is smell, sense of smell or something like that. How can I couple these different stimuli to light up some particular spot in the network, right? It's a very hard problem because there's an infinite number of ways you can do this, but it's something that we can play around with today. What pathways permit signals to propagate through? Yeah.
Okay, so this is a similar question. I was judging the poster at Rice University, and the student did is, the son of the student has some slow speech. Mm-hmm. So instead of visual, he's doing the speaking. Okay. So when you try to talk, like right now I'm thinking, and then I compose, and then I speak out. Yep. So it activates different part of the brain. Yep. It can show the different activation. But that is just like you say, put another eyeball. So actually, there's the input into the upper layer of your hierarchy. Mm. Instead of, so it's a sequence of actions. And also, I have seen a show like maybe Discovery or Nova. It was talking about in our cognition, there are two parts. One is the visual detection. Mm-hmm. Let's say, well, I see you. You look like my brother, but then I don't feel like you're my brother. You're totally pretending my brother. Yeah. So it's the emotional part of in the hierarchy that is make you associate. So there was a guy, he actually had brain damage and then broke the emotional part. Yeah. So he kept running away from the home, he said, well, I see my mom, I see my house, they look like it, but I don't feel it.
Yeah.
So I don't think they are really my relative in my home. He ran away.
Yeah.
So maybe in your hierarchy there are different
So,
area. You have visual and then you have emotional.
yeah, that's 100% the case. So in a much simpler case, this is the salamander eye once again. And basically they're showing it a picture of a salamander under the assumption that salamanders recognize salamanders. But basically the input is the timing of the spiking pattern. And the inference that means something has to come from the inside of the network, right? And so if you were to break some wiring upstream, you'd still see the signal. You can still see your parents' house or whatever. You can see your brother. But if you traumatically rewire regions of the brain, you can completely destroy the ability to interpret what you're seeing in a physically meaningful way. That's absolutely true.
Say one is longitudinal. This one is the sequence of events, and the other one is kind of you derive from the original input and how to come up. So there are two different ways of how you progress with the hierarchical structure. Yeah. Another thing is there was another professor. I invited him to our campus after that. So what he did is Bill Collins is that he showed a lot of like illusion type of thing. So like for example, you will compensating or you will have some kind of distortion just because our mental tries to rebalance it or something. So actually we'll see something is not there. Yeah. Yeah. So I guess you can study that part with
So
to interpret how it works.
Yeah. So because you have these downstream structures that interpret the thing that you're shown, if you're shown something that doesn't that your eye doesn't respond to well, so if the physical interaction between the light that you're seeing, the retina, if the downstream interpretation network isn't robust to what it is you're seeing, it's going to do something with it. In the same way that I was able to convince at least some of y'all that there's structure in this, there isn't. There's just nothing there, but you can see it. And the reason why is because your brain has to interpret what it is that it's seeing, right? And so, so if you're shown optical illusions, the brain does something with the thing that it's seeing, and it does something incorrectly. Because of the way that's.
One example would be he'll be showing this, and then everybody will say, well, that is darker, that's lighter, but it's exactly the same intensity, but because the background is different. And so it causes you to have different judgments.
Yeah, I'm colorblind, so those don't affect me. But okay, any other questions? Okay.
Let's thank our speaker.
And thank you at home.
And also have your papers in the front here for everyone who didn't collect them yet. And I still need to get a few more from you guys. And also for the graduate students, if you haven't already, I'd like to get updated drafts from you guys. We'll look at those.
Okay. Yeah, I'm not sure. Oh, sorry. It'll comment in a second.
Yeah, hold on. I just want to end the recording.
Yeah, I know my